Any process of the fabrication of aluminium components determines not only the shape of the component, but also its microstructure. In turn, the microstructure determines the component's properties. Certain properties of aluminium are largely independent of the content of alloying elements and the processing chain. They are the modulus of elasticity, the density, and the thermal expansion coefficient. Most other properties are very sensitive to the material's microstructure and composition. As indicated in this figure, it is natural to divide these properties into 4 categories: strength, ductility, and formability, fatigue resistance and fracture toughness, high temperature resistance and creep resistance, corrosion resistance, wear resistance, and surface condition. The alloy composition, the shaping processes, and heat treatment determine the microstructure. The microstructure, in turn, determines the properties mentioned above. Aluminium has a face-centered cubic lattice structure. The atom's relative position in the lattice arrangement will remain the same as long as there is no plastic deformation of the material. If the material is strained enough to cause plastic deformation, certain crystal planes slip in particular directions. Dislocations form when crystal planes slip, and their migration contributes to the material's strength and ductility. Manipulating these factors optimizes properties. When subjected to plastic deformation, dislocation sources will be formed inside each grain under the influence of external forces. The metal is strengthened by the deformations. The work hardening has reached the saturation point. The curve will flatten out as indicated in this figure. Heating will cause disappear. It gives the possibility to achieve the desired combination of strength and ductility through a partial annealing or back annealing. When alloying elements replace aluminium atoms, they form solid solutions, enhancing the material's strength by impeding dislocation movement. During solution heat treatment, oversaturated alloying elements precipitate as intermetallic particles, forming a needle-like structure that strengthens the alloy. Rapid quenching prevents diffusion of alloying elements, creating an oversaturated solution. This process strongly influences the alloy's final properties. Artificial aging involves heating the alloy to promote controlled diffusion of atoms, resulting in increased flow stress, but overaging can lead to a reduction in strength. As time goes by, alloys can naturally age and display variations in their properties, particularly in zinc and magnesium alloys. Solidification creates grain structures, forming the cast structure of the alloy, crucial for its overall integrity. Wrought alloys undergo additional processing, enhancing grain structure control through recrystallization, leading to further mechanical property improvements. Thank you for watching. If you enjoyed this video, please like, comment, and subscribe for more content.